topic we're going to talk about today is one that we would normally cover pretty quickly in class. But we have the advantage here of doing this online so we can slow down and give this topic a bit more of the attention it deserves. This is a really beautiful topic. There's some great stuff here, and I'm glad that we can go a little more slowly through this and think about this a bit more than we normally would. Here's what we're going to be doing. We have up until this point talked about how you get a potential energy function from a conservative force. So we know how to take a conservative force F and obtain the potential energy function that's associated with it. What we're going to do today is to go in the opposite direction. We're going to assume that we know what the potential energy function is, and we're going to go the other way and find the conservative force that's associated with it. Now, to set up a little bit about why this is such an interesting thing, let's look at what's happening here. In the first case, we're moving from a vector quantity to a scalar quantity. And the way that's done, if you'll remember, if you have a conservative force and you want to find the potential energy function, what you do is you evaluate the work along some path. Here's the work. And in the process of doing this dot product, all of the vector quantities disappear and you end up with a scalar quantity. Now we need to go the other way. We need to go from a scalar quantity and end up with a vector quantity. Since we're going in the opposite direction, you might imagine that we need to do the opposite operation. I'm going to take you through exactly how this goes, but let me tell you now what the answer is, and then we'll explore it and think about it a bit. If you want to go from here to here, we need to do the opposite of what we did over here. Instead of integrating along some path, we're going to end up taking a spatial derivative. We'll take a derivative, and it's a special kind of derivative that takes a scalar function and turns it into a vector function. It's a kind of derivative called the gradient. You end up calculating minus the gradient in the potential energy function. What this gradient function does is it finds the direction that the function is minimizing in. If you imagine walking along some mountainside or some hillside, at any point when you're on the hill, there'll be a direction that is straight uphill, where the potential energy increases the most, and there'll be a direction that's straight downhill, in a direction that the potential energy, due to gravity, decreases the most. That's what this gradient function does. The gradient by itself shows you in what direction and how rapidly the function increases. When you put the minus sign in front of it, it shows you the opposite. It shows you what direction the function decreases most rapidly. And as it turns out, that is the direction of the force. Whenever you have a potential energy function, it turns out that the force is always directed towards the minimum in that potential energy function. Let me sketch here an arbitrary potential energy function. Maybe this is the x-axis, and this is potential energy U. If the potential energy function looks like this, then at any point, you can evaluate the derivative with respect to x of this potential energy function. It's the slope of the line tangent to the path there, and in this case, it's positive. So this term would be positive. Put a minus sign here, and that tells me that the force is going to be negative. So the force on the particle at this point is in the negative x direction. If, on the other hand, we were over here, where the slope is negative, then that negative derivative times this negative out front is going to give us a positive force, and you can see that no matter where we are, the conservative force on this object is always going to be forcing it to the bottom of this potential energy well. And that, as it turns out, is a universal principle that applies in nature. When you have an object, the force on it, if it's a conservative force, is always going to be directed to the bottom of a potential energy well. Once it gets there, to the bottom, the derivative is zero. That's a horizontal tangent there. So there's no derivative of the potential energy function, and so there's no force. That means that this is what's called an equilibrium location. So where there's no gradient, where there's no derivative to the potential energy function, there's no force. Now suppose we were over here. At this point, the slope of the potential energy function is positive, so the force would be in the opposite direction. And again, the object is going to be directed to the bottom of this potential energy well. Again, where there's an equilibrium point. The particle might pass through there and oscillate up and then back around and oscillate around that equilibrium. Or if it's over here, it could oscillate around this equilibrium. But it's always being driven to the local minima in the potential energy functions. There are other equilibrium points than the ones I've shown here. This point right here is also an equilibrium. The tangent there has zero slope, so there's no force. And the same thing here. Any local extrema in the potential energy function gives you an equilibrium point where there's no force. But you see there are two kinds of extrema. There are minima and there are maxima. Here, the second derivative of the potential energy function is positive. It's concave up, and that tells us it's a point of stable equilibrium. This means that if the object is at rest here and we perturb it, it'll oscillate around this point like that. Up here, the second derivative of the potential energy function is negative. It's concave down, so that it will sit there forever unless it gets perturbed. And if I perturb it, it'll slide and not come back. That's the difference between stable equilibrium here and unstable equilibrium here. If it's stable, you can perturb it and it will oscillate around that point. If it's unstable, you can perturb it and it'll go away and not come back. Okay, so that's the idea. Let me show you how this works out. What I want to do here is assume that we know this potential energy function, and I want us to think about how we can find the force from it. This is the result we're going to end up with, but the story of how we get there is an interesting one, and in your training as a scientist or an engineer, this is a good lesson to hear and to learn from. Let's start by writing down the work done by this conservative force. F dot ds along some path is, as we know, for a conservative force, minus the change in the potential energy function u. All right, now rather than integrating this force along some path, integrating it from say here all the way to here, let's look at one step along the way. So one single contribution to this integral, just F dot ds. That will tell us not minus some finite change in the potential, but minus some differential change in the potential energy. So minus du. The left-hand side I can expand using the dot product, and I can write this as fx dx plus fy dy plus fz dz, and that's minus du. So we see that in 3 dimensions, there are 3 contributions to changes in the potential energy function. You could be moving in the x direction when there's a force in the x direction. That's what's happening here. If you move in the negative x direction and the force is in the negative x direction, then the potential energy is going to go down. That's what we talked about here. And here, if you move in the positive and the force is in the positive, this minus sign tells you that the potential energy will go down. So there could be a force in some direction and you move in that direction for the x direction. Or you could be doing that for the y direction or the z. Each of those 3 things independently contribute to minus the change in the potential energy. What I need to do here is to dig out from this expression those individual contributions. I need to figure out what fx is, and then separately what fy is, and separately what fz is. I don't want to know their whole contribution together. I want to know the individual components. So how can we find fx? The way to find one of the components, let's go for fx first, is to say, let me look at how the potential energy u changes when I have a force in the x direction and I move in the x direction, but I don't move in any of the other directions. So I'm going to set dy to 0 and dz to 0. And now we want to know how the potential energy changes when we move in the x direction and there's a force in the x direction. The other components are 0. The other displacements, I should say, are 0. We can solve this for fx, and it's minus du dx. So the x component of the force is minus the derivative of the potential with respect to that component. But it's important to note that that's only true if these contributions are zeroed out, if dy and dz are both equal to 0. So before you can isolate the contribution of the x component of the force, you have to zero out the displacements in the other directions. This derivative, where we take a derivative with respect to one variable with the other ones not varying, being held constant, is a special kind of derivative that we call the partial derivative. This is minus du dx. And this curly derivative sign indicates that you're holding the other variables constant. This is minus the derivative of u with respect to x, and it means holding y and z constant. But if you do that, you can find fx. The same thing happens if you're trying to find the y component of force. Suppose we were after this guy. The way I would do it is to look for changes in the potential energy function when I move in the y direction due to a force in the y direction, but I'm going to not allow x or z to vary. So I'll get this. And that, as before, is minus the partial derivative of u with respect to y. Again, the partial derivative with respect to some variable means hold the other variables constant. Same thing for z. If you want to know the z component, you're going to look at how the potential energy function varies as you move in z, holding the others, x and y, constant. And that is the partial derivative of u with respect to z. All right, so there are the components. What I want to do now is assemble those components together into a vector and rewrite this in a form that gives us this result that I told you at the beginning. So let me erase what we have here on the right, and we'll assemble those components and do this. All right, so the force vector is the x component minus du dx with an I hat to make it a vector. The y component is du dy with a j hat, giving us that direction, minus du dz with a k hat, giving us that direction. So here's our force vector now. Fx, Fy, and Fc. We can rewrite this by factoring the minus sign out to the left and factoring the potential energy function u out to the right. That gives us minus I hat d by dx plus j hat d by dy plus k hat d by dz, all operating on the potential energy function u. This thing in parentheses is a vector differential operator. It's a vector because of this I hat, j hat, and k hat. And we say it's a differential operator because of these derivatives here. And it's going to operate on the potential energy function. If you do that, what you get out of it is the force. This thing has a shorthand name, and we call it del. So instead of writing all of that in parentheses, we just write del. So the force is minus del u. And del u is what we call the gradient. We call it the gradient for the reason that I mentioned earlier. Imagine you're on a hillside, so that there's a direction that goes up the steepest and one that goes down the steepest. What this gradient operator does is it takes a potential energy function, a function of the height in the case of a mountainside or hillside, and it finds a direction in which the function varies the fastest. It finds the direction that's up as fast as possible, uphill direction. And then the minus sign sitting in front of it turns that around and takes you downhill. So gradient of u finds the uphill direction from these derivatives. It finds what direction the function changes the fastest in. And then the minus sends you in the opposite direction, and that's downhill. And that's why it is that no matter where you are, you always end up getting pushed downhill to the bottom of these potential energy functions. When things in nature are moving under the influence of conservative forces, they always get forced to the minima of their potential energies. Potential energy tends to be minimized in nature because that's the direction that the force is always pushing in. Okay, to avoid making this video too long, let me do this. Let me stop this one here, and in the next one, we'll look at several examples. We'll look at some potential energy functions that we know, and we'll get some practice using this gradient operator there. And then we'll look at one that's just an arbitrary made-up one that we can practice with. Okay, so I will see you over there.